Hi, good morning. This is Narari. Today we're going to talk about a quick method of estimating the wing bending moment and shear force, especially during conceptual design phase. I have collected most of the material from open and public domain sources, and I make no claims either explicitly or implicitly about originality. Video is purely for educational purposes only. A conceptual design overview. A new design for an aircraft is launched when it is perceived that there is a requirement to fulfill a need beyond the capability of an existing aircraft. And this could be, to ensure that whatever aircraft you have do not operate at, let's say, high altitude or at very hot conditions. So you are looking for an alternate design. In some of the aeronautical applications, the need arises because an existing aircraft is coming towards the end of its useful life. An example being the MiG-21, which is there in the Indian Air Force. It's been serving the Air Force pretty well from past 3 to 4 decades, and it's time to now move on to different aircraft. Or the aircraft design, whatever you have, has been overtaken by developments in technology. This usually happens either with the new materials which can be used to reduce the weight of the aircraft, or new electronic warfare equipment. And in some cases, there is an operational experience. That is, you have an existing aircraft, you have used it, and you have found that there are some cases where it is falling short of your requirements. Or in case where you see a potentially unfulfilled exploitable need, and that is identified, you come with a new design. The last one, for example, I can give you in cases where, especially during the Kargil war, it was realized that at that high altitude and at that atmospheric conditions, most of the aircraft, especially helicopters and others, have difficulty in working. So there is some need for it to be new kind of modifications or new design itself to be undertaken. To give you a simpler example, which most of us have realized, you take the case of Maggi noodles. Nobody had ever heard of a 2-minute noodle before. They somehow identified that there is going to be a need in the market for such an odd-looking product, and they came with that, and see what happened. The rest is history. So, if you can identify something which you can exploit, and you know there is a need for it, that also would lead to a new kind of design. And most of the design starts with the user giving you a set of requirements. These requirements can be very brief and very cryptic. And usually the requirements could be performance or some other requirements. Sorry. In this case, I've just listed an example of a military trainer. This is a basic military trainer in the sense that when the pilot joins the Air Force, he goes through a simple training and then he advances to combat kind of training. Of course, they don't put him directly on fighter aircraft. He goes into somewhere in between fighter aircraft and a basic trainer to military trainer, which can do high G maneuvers. It can fly fast and things like that. In this case, the requirement was for a takeoff mass less than 2,800 kg. It should be able to withstand load factors of 6 and -3. It should be able to fly at least 6 kilometers in above altitude. It should be able to stay in the air for 3 hours or more. It should have a rate of climb of 1,000 feet, 10,000 feet per minute, or roughly 50 meters per second, and its glide angle should be less than 10. Each one of these will give you an indication or a hint of what needs to be done with the aircraft. For example, if I say glide angle is less than 10, you have seen from the performance studies you have done in your classes, glide angle is decided by L by D largely. So very high L by D means very low glide angle. So if I say less than 10, it will tell me what should be the minimum lift to drag ratio I should expect from the design. So many of these things are derivable from this. Key requirements generally are performance requirements. That could be range or sortie pattern with basic payload. So you are told that with the basic payload of, let's say, if it's a combat airplane, minimum 2 missiles and 1 bomb and ammunitions. Or if it's a commercial airplane, it should be able to seat so many people with this amount of luggage, and it should be able to fly this distance. Or in combat aircraft, you should be able to fly the distance and come back, in which case it is called radius of action, not range. We should be able to find out what are the alternative combinations, range, payload combinations, and especially with fuel reserves and additional fuel. Is it possible, for example, to extend the range of an aircraft by carrying additional fuel in drop tanks, basically disposable tanks. You should also be able to find out whether the minimum and maximum and cruise speeds are meeting the requirements of the user. The user can also say takeoff and landing field length limitations. Typically, a combat aircraft has to operate in forward bases, which are not international level runways. These are temporary bases, and you should be able to take off and land in very short field lengths. Climb performance such as the time to a given height and service ceiling or operating altitude, these are basically coming from combat requirements. The climb to performance essentially comes in when you detect an enemy aircraft coming and you like to go and intercept it, in which case you should be able to go to that altitude as rapidly as possible. And service ceiling comes in when the enemy aircraft is flying at an altitude, very high altitude, let's say 12, 13 kilometers altitude, whether your aircraft is able to reach that altitude. There are also certain performance maneuver things like how fast it can turn, what is the sustained turn rate, what is sustained turn rate, acceleration requirements, and things like that. For all performance requirements, design of the wing is the key factor. Wing is the one which is the fundamental working device in an aircraft. A part of the aircraft which provides lift, supports the entire aircraft and its contents while in flight. You need to sometimes, if you're given, for example, in the case we were told that it should be able to sustain 6 times the load, then need to support n times the aircraft where n is the load factor. It doesn't end here. Based after this, there is something called factor of safety, which could be 1.05 or 1.1, or in some cases 1.2. That multiplies the load factor. So it will be 6 into 1.2, for example. And we also have design options where we place the wing, high or mid or low wing. Each one has its pros and cons, and you have to be able to decide based on the requirements and how the design evolves. It could be a single wing, and most of the planes now are single wing monoplanes. There are cases where there are aircraft with 2 wings, biplanes. In almost all cases, except rare cases where the braces are used that support the wing, wing structure can be treated as cantilever, anchored to the fuselage structure. So if you look at the position of the wing, as I said, you can have low wing, and most of these commercial aircraft, you can see the Boeings and Airbuses, which you see in our airports, they all are low wing. Wing is low, below the center of gravity of the aircraft fuselage. You also have mid wing, where the wing is close to the center of gravity of the aircraft, as in this case. And you also have what's called a high wing, where the wing is almost at the top of the fuselage. As I said earlier, in all such cases, it is treated as a cantilever fixed at one end of the fuselage. That one end could be where it attaches itself into the bulkhead in the fuselage. And bending moment and shear force at that joint is what we are interested in computing, and this talk is related to that. So design of the wing, let's have a quick overview. Wing design starts with estimation of the wing loading parameter W by S. Based on historical data, you can look at similar aircraft as to what kind of wing loading they have used, and also you can use what's called a constraint diagram, which is a plot between TW, thrust to weight ratio, and wing loading plot to arrive at an estimation. The first, you can say value for W by S and T by W. I have a separate video on how this constraint diagram is derived and how you use the performance requirements as constraint. That's why it's called constraint diagram, to reduce the design space where you have T by W and W by S. So I request you to watch that video to give more details about constraint diagram. And then follows what's called the plan form. Plan form or aspect ratio, root and tip chord, sweep, leading edge or quarter chord, and trailing edge sweep, taper ratio and twist. All these are very crucial parameters. It's not enough if you simply have the area of the wing, which comes from the W by S and W, but you need to be able to come out with the plan form. And then once the plan form is decided, you look at the cross section of the wing, that is the airfoil, based on dominant requirements. For example, in a passenger aircraft, choose such that the cruise seal falls in the drag bucket region of that airfoil. If you look at normal airfoil bases, for example, the Illinois University has a base of database of airfoils in which all airfoils data is available, CL versus alpha, CL versus CD. Some aircraft, you feel that for a small range of CL, the CD doesn't change much. It's a flat Z. That's called the drag bucket. So if you are looking at a passenger aircraft, which flies at the cruise condition for a long time, and that's where you would like to minimize the drag as much as possible, you choose an airfoil which has a drag bucket in that range. Of course, in a combat airplane, these things don't apply, especially fighter planes, because they have to fly at whatever altitude, whatever Mach number is required during combat. So, in a combat airplane, you try to look at the maneuver conditions, okay, high angle of attack performance, and all those things for airfoils. And also, you have to select high lift devices which are deployed only during takeoff, landing, uh, to increase the CL max of the aircraft. And some combat airplanes, there are also what are called maneuver flaps. Tejas, for example, has the leading edge flaps which are used during maneuver only. And configuration of the wing is fundamental to the design of the aircraft because everything else comes after that. So the interaction of many parameters involved in the wing design can be described under airfoil section using high lift devices, planform shape, geometry, determined by the operating Mach number of the aircraft, airfoil shape, overall size, that's wing area, decided by the planform and airfoil section. So all these things have to be changed. The number of variables which can, design variables which can be changed are enormous. So overall size of the wing area decided by the planform and airfoil section. So there are a lot of parameters which needs to be changed either together or one at a time or multiple combinations. So in such cases, every time you change, let's say the aerofoil, the geometry of the wing cross section changes, and every time you change the planform, overall area changes. So what actually happens is that every time you want, if you want to create a high fidelity geometry, let's say based on the CAD software, which is needed if you want to run the CFD, it's not feasible. You don't really have the time to do this. Just an example, during the Tejas design phase, and I was there in France, the Dassault systems at that time, we spent about 3 months in freezing the wing, and close to 40 to 45 wing different shapes were tried out before we zeroed in on the final configuration. And every time it would be decided, and we are using low fidelity codes to estimate the forces and loads coming on that, and also quickly estimate the bending moment and the shear force at the root. This was needed because there was at the same time there was a team from structures group whose job was to take the bending moment shear force from our end and then come out with the design, structural design of the wing. So this has to be done concurrently so that they could tell us that whatever you have chosen, it's not feasible or it's okay, so that we could go ahead further. Just an example, if I'm looking at transonic design of an aircraft, I would choose a very small thickness to chord ratio because that will give me a higher angular performance. But a small thickness to chord ratio has poses huge challenges to the structures group. So it has to be done together, and that's what we were doing earlier. So several wing layouts were tried, planform, aerofoil, leading edge, staging edge. Choice of this above is decided primarily by aerodynamic performance. It's essentially CL max that will tell you how the landing and takeoff distances, and L by D, which will tell you the overall performance, including glide and other things. CL versus CD, that will tell you what is the it's called the drag polar. It will tell you how the drag will increase and the thrust you need to overcome that. And then of course there's a crucial thing called CD naught versus Mach number dependence. I also seen that the CD naught varies very rapidly with the Mach number, especially when it crosses the transonic conditions. In most combat airplanes, the CD naught is somewhere close to 0.03 till about Mach number of zero point 0.8, and above that suddenly it goes up by a factor of 2 or 3. So, and because of this consideration of transonic drag race, we may want to have as low a T by C or thickness to chord ratio as possible. Wing weight is of course proportional to 1 over root of T by C max. This is a thing which has been given to us by the structures group. So every time I reduce the maximum thickness to chord ratio, the wing weight increases significantly. So if my T by C instead of 12%, I took 6%, the wing weight will go up by 41%. So very low T by C means, of course, also reduced space for structure and fuel storage and a whole lot of other issues. So continuous interaction with structures group is essential, which is what happened in this case of Aegis as well. Wing weight is typically 15% of the total empty weight of the aircraft, so it's not a small factor, contributor, and we need to be very, very careful doing that. Since several changes are expected, as mentioned earlier, only low fidelity geometric definitions are used instead of detailed CAD models. What I mean by low definition is, airfoil definitions are given for a chord length of 1 meter. So I decide on the plan form and then scale the airfoil at that chord, local chords, and then loft it into a simple surface. It's not the same high fidelity surface as you get in CATIA or AutoCAD or any one of those CAD surfaces, but enough to be able to run the low fidelity aerodynamics code which we were using earlier. And since the definitions are not accurate enough, CFD and FEM analysis of structure are therefore not feasible. Structural design also needs to be doing on the same time, and they need loads, estimated loads with increasing fidelity as the design cycle. So initially it was enough for us to tell them that this is the maximum bending moment and shear force which is going to come at the root, and they would come out with a design. Either say yes or no, basically go or no go for our design. Bending moment and shear force estimation and torque as well is of course consistent with the fidelity of the geometry are required. So one such technique which came out somewhere in 1930s or a little earlier or later, I don't quite know, is called what's called Shrenk's method. Shrenk is a researcher who came up with this method of estimating quickly. And this is a quick recap of the cantilever. So you have a cantilever, which is in this case, let's say it's a fuselage, and this is the wing attached to it. And you have a bending moment and the shear force which is coming at the root, which is what I'm trying to estimate. Okay, now let's look at the ultimate load on each wing. The ultimate load on each wing is the weight of the aircraft into maximum load factor it's supposed to take. In our case, it was 6 in the example case, but it could be anything. It could be 8 in combat airplanes. Multiplied by 1.5, that's the structure safety factor, divided by 2. 2 because, one half of it is on the left wing and half on the right wing. So this is the maximum load which is coming in. The question is that load distributed like as I've shown here, or is that load a point load acting at the tip or somewhere at the centroid, or we don't know. And depending on how the same load is distributed on the wing, the bending moment will vary. Shear force will be the same, that's the load itself, but the bending moment will vary significantly. So for any span station, the shear force is simply the sum of the vertical loads outboard of that station. So that is part of the easily computed. Bending moment at any station equals the sum of the product of load at each outboard station and its distance from the station. For a positive bending moment, the internal forces produce compression on upper part and tension on the lower part. This is, you can say bending moment and SFD 101. So let's start with the crudest method possible, or what I call a level 0 estimate. The first estimate of maximum load to be carried out, as I showed in other diagram, is for a given load factor of 6 and a factor of safety of 1.5. The maximum load will be W, weight of the aircraft, not mass, weight of the aircraft, into 6 into 1.5 in the positive direction, that's upward direction. And load in the negative direction is W into 3 to 1.5. So load on the left and right side of the wing is half of the above. Now let's make an assumption. I have just shown a simple trapezoidal wing here with a taper ratio. Of course, wings should are not as simple as that, but this is just for explanation. Assume the lift to be a point load acting at the centroid of an arbitrary tapered wing. This is an assumption. However crude, but I'll show you later, it's not that bad. In a trapezoidal plan form, you can easily find out what's the centroid. So load you have got the centroid location. Now that will tell you then the shear force of the wing load is maximum load by 2. Okay, that's the wherever the load acts, the shear force is fixed. That's the maximum load coming at the joint. The bending moment then would be y centroid, that is this distance, into maximum load by half. Okay, so this is the bending moment, very, very crude bending moment. Now, if you're interested in what's the torque coming, you have to make an assumption where the joint is likely to be. The joint is likely to be, the leading edge or the trailing edge or in between. So making that assumption, you also have the distance in the other direction. You should be able to estimate the torque. Now this is, as I said, a very, very crude method where you have assumed the entire load is acting uniformly and you have found a centroid and all that. But as I'll show later, that's not that bad. You can easily, you can get away with close to 20% accuracy. Now let's look at the realistic lift distribution. Here you have an aircraft with a low wing configuration, doesn't matter low or high, just for illustration. The lift you can see goes to a peak somewhere here and then drops down to zero at the wingtip because there is no structure here, and there is a pressure which comes from flow which comes on the bottom top. There's a tip vortex and all that, so it reduces to zero and then it drops near the fuselage. So this is how it is. The reduction near the center line and the fuselage effect tips because of that. A blended wing design, which people are talking about now, reduces the fuselage effect significantly, but they are still a little way away from commercial deployment. Wing devices reduce reduction near the tip. So you can see some aircraft have small extension of the wing pointing upwards or pointing downwards, or simply a flat plate at the edge, which can reduce the losses. But the key point is the load is not uniformly distributed from wing root till wingtip. Okay, that's the platform thing. What about from leading edge to trailing edge of the wing? Now here is a data from somebody else's computation, which is available in the open domain. This is the pressure distribution on an aircraft wing, generic aircraft wing, and you can see here this aircraft has a sweep back. It's nearly trapezoidal except for a small extension here, which is called Yehudi. And people have computed the CP, which is of course the load indication of load, the coefficient of pressure on the upper surface and the lower surface, and you can see from root to tip it varies significantly. They are not uniform. So you have two issues now. The load is not uniform wing root to wing tip. Load is not uniform from leading edge to the trailing edge. So these are the two variations which are there compared to our level 0 method. So in the Schrenk's method, you try to address, can we do something about taking this variation into account? Okay, so what we start off with using the high CL max limit, basically maximum dynamic pressure for load calculation on the wings. Span-wise distribution is proportional to the circulation at each span station. So this is an assumption which comes from aerodynamics. I know wing exact lift is produced by circulation, and you can say that circulation depends on the local span station, basically the card. So okay, and for an elliptical planform, the distribution is elliptical. Elliptical planform is if you take the card from root to tip and plot the lengths, then it turn out to be an elliptical quadrant. And just as a matter of interest, the Spitfire aircraft, which was very successfully employed by the British during the World War II, had this classical elliptic platform. But later it was realized that fabrication was a challenge for elliptical platform, and it was quickly found out that a tapered wing was as close to elliptical platform as possible. So roughly a taper of 0.3 to 2.5 to 0.3 would give you as close to an elliptical platform as possible. And since it's only a taper, it's pretty easy to lay out and fabricate. So now nobody uses elliptical platforms anymore, but just for the thing, elliptical platform as the most efficient aerodynamics part of it. For non-elliptical wings, Schrenk's approximation or semi-empirical way to estimate the lift distribution is used. So the statement is load distribution on a wing is the average of the actual platform shape and the elliptical shape of the each span and area. So this is the statement given by Schrenk's report. A quick note here, Schrenk's method is not applicable to highly swept wings such as delta wings like Tejas or Mirage 2000. Because of the vortex flow, these wings have a different kind of loading structure. But for most of the commercial airplanes where the wing sweep is close to 30 degrees and there are no funny vortices around, this can be used. Sorry. Just way to see that if you have a wing like this, a generic trapezoidal wing where the root card is given a CR and the tip card is given a CT, and semi-span is B by 2. B is a span and one side of the wing is B by 2. The taper ratio is CT by CR, tip by root. And as I said, taper ratio of close to 0.25 to 0.3 gives you an optimal as close to the elliptic loading as possible. And here are some other things. So what I have done here is I have taken the wing and split it into strips. Each strip has an area of delta SI. Overall area is S by 2, half of the wing, total wing area. And each strip has delta SI. Okay, and each strip in this case is a trapezoid. It's easy enough to find the area of a trapezoid. And each place you can estimate the chord. You can actually compute the chord given the leading edge and trailing edge angles. So I'm treating each strip area as delta SI and each chord as CI, C of I. And when I is equal to 0, that is the root chord, I is equal to D is the tip chord. So I just make the strip areas. Now again, let's go back to the overall maximum load, Wn into Fs by 2. Fs is the factor of safety. If I distribute the chord in a trapezoidal form, that is root chord into 1 minus 2 y by b into 1 minus lambda, and here the lambda is the taper ratio. So as we say that if the taper ratio is 1, that means it's a rectangular wing, this factor goes away, CR is same as CT. Okay, and if the taper ratio is 0, then tip chord is 0. But as I said, taper ratio generally varies between 0.2 to 0.3 most commercial airplanes. The elliptical distribution of chord is a quadrant of an ellipse. You just take this equation on faith from me. Okay, and you take the average between these two chords, trapezoidal chord and the CI ellipse chord, elliptical chord, and then multiply by the delta yi. That basically the you can say that area of the strip. Area of the strip is average between these two chords. This is it into the width of the chord, which is delta yi. So on the load factor you need to find out. You have maximum load and maximum load divided by all the strip area. This comes out as Newton per meter square. So load on each strip is delta SI into load factor. So this is how you compute the load factor. As a quick note here, I have a complete worked example in a spreadsheet in the shared drive, and the link for that is given here. And moreover, if anybody is interested in getting that Excel spreadsheet, you drop me a mail. I'll have put my email at the end. You just drop me a mail and I'll send it across to you. There is no difficulty in that, so that you can work around with it. Okay. So in the example, what I have done is I have taken the Airbus 330 by dash 500. It's a common, pretty popular aircraft, and I have the data for that also coming from open domain. Maximum, takeoff mass is some numbers, and span is 61.2 meters. As you can see, it's pretty big aircraft. Wing area is 437 meters square. Just to give a comparison, the span of Tejas is only 8 meters. This is like 61 meters kind of thing. Okay, and taper ratio, as I've been telling, is around 0.22 in this case. I have not taken the tail lift. You can take the tail lift also included here. Since I didn't have the data, I have not included that here. So the maximum lift I have used as before, this mass into 3.5. 3.5 is the safety load factor every commercial aircraft has to be designed for. It's not that they are going to fly at 3.5 Mach G or 3.5 G load. It is that the structure has to withstand that. That is, the N is 3.5 for commercial airplane. Now, if this was combat airplane, all these numbers will be there, and this N could be 6 or 8 depending on the requirement. Okay, so as I said, we have assumed a simple tapered wing shape for, but of course the actual Airbus wing is more complex. It has a sweep and also a Yehudi at the railing edge. But suffice to say, for computing, for explanation, this is what it is. Okay, so let me see if I can open the Excel in this. I'll just explain what I have done in that Excel spreadsheet, and then of course you can download it and then try out different kind of loads or any other aircraft you are using in your project design or just for the curiosity. Okay, so here is a spreadsheet which has data for different Airbus aircraft from A300, 600D to 321, 330, whatever I could find in the open domain. I have collected different data for, of course, not all data is available. Whatever is available is there, but enough for us to be able to do our computation and test out the thing. Now, when you are designing your own aircraft as a project work, then you can stick all the numbers you have in this. Okay, here is the data as I was shown earlier. 365,000 kg is the mass of that aircraft. The root chord is 11.71 meters, taper is point, all that. So now let's start by dividing the wing into about 30 or I don't quite remember how many, maybe 30 or 50 strips. Yeah, about 50 strips are there, and each one I'm starting from the tip. So the tip value would be 30.6, it goes right down to 0. Okay, and at that point I am taking the card, that's 2y by b, span station. One is the tip and 0 will be the root. The card I am computing, tip card is the 2.577, that's the tip card, and if you go down to it, the root card will be what is the number given here. Okay, now I'm going to distribute this trapezoidal chord here based on this equation, which is a very simple one. And the elliptical chord, I'm going to use this equation. Sorry. Okay, so in this equation, the elliptical chord comes with 0 and goes right up to a slightly different chord than what is the actual chord. So the Schrenk's approximation is take average between these two. That is, add these two and divide by 2. That will be there, and then you have delta y. Since the first point is the tip, strip itself is in, you have to go to the next point. So elemental chord at that time, elemental area, that is delta SI, and the shear force load coming on that, and then bending moment. Bending moment is that force into the distance from the root. So you can go right up to it, and if you plot the bending moment, sorry, if you plot the bending moment, it shows up like this. Okay, from the root to tip. Similarly, you have shear force diagram, and to check how accurate or whether there has been any errors, you do a quick sanity check. Now we have computed the strip areas of all the strips, right? So, and you can look at the adding all the strip areas as to how much, what's the strip area you come out with. And that shows up as 218.65, and is almost exactly the same as what you started off with. There will always be some error, as I said earlier, but you need to find out what's the error. Okay, maximum load, if your computation maximum load is 136, whatever that number, and the maximum load, what you get is this. So there is a 0.04% error. It's pretty good. And from this, you can see what is the center in which the force is acting, center of force action. That turns out to be up to 6.227 meters. Okay, so I'll quit here. So Schrenk's approximation, basically, to explain it figuratively, if you have a rectangular planform and you have a tapered planform, so rectangular planform means roughly the span load is constant across. It is not the tip, of course, there will be losses, but you have made an assumption it is constant, right? And elliptical planform, it will be 0 at the tip and go to the maximum and come back. And the Schrenk's approximation is in between. Okay, now if it is a tapered planform, the load, of course, you have assumed that load is proportional to the tip chord, so it's not 0 or constant. It is varying from ratio between tip chord to root chord. Maximum at the root and lowest at the tip. And elliptical, as before, is 0 at the tip going back, and average is in between that. So this is the Schrenk's approximation, and this kind of shear force and bending moment you get. Okay, I'll stop here, and thank you for listening to me. Please send your comments, suggestions on the presentation to my email ID, narahari.ruas@gmail.com. Let me know if there is any particular area or topic you would like me to address, and I'll try and see if I can do that. Please subscribe to my channel and press the bell icon. A complete worked example in a spreadsheet is available on request. Please drop a mail to the above mail ID. And thank you, and goodbye.